So now we start with video lecture 12 and this will be the last video lecture for this week. Today we start a little bit about the energetics of solid solutions. Energetics of solid solutions. We consider our discussion based on a binary solid solution. So what does this mean is, let's say you have a mineral A, B, X. So the two end members are AX and BX. Or we name this as, for our discussion, as A and B end members. So we start with a phase AX, ABX, of which there are two components, AX and BX, and these are called A and B, phase components of AX and BX. Now, we know that there will be something like GA is equal to GA0 plus RTLN activity A, and we know that there should be GB is equal to GB0 plus RTLN activity of B. We also recognize that A is equal to X into gamma. We also realize that A is equal to X into gamma. Now, we have been talking about this, but at a particular pressure temperature, G0B is a constant. At a particular pressure temperature, why? Because as per our definition, G0 is equal to H0 minus TS0 plus P into V0. That's our expression. So if we know temperature and if we know pressure, then the whole term essentially is a constant. Similarly, for GB0. So now let's draw a diagram where and we write at known pressure and temperature. And this is A and this is B. So if you think XA is equal to 0 here and XB is XA is equal to 1 here, which means XB is equal to 1 here and 0 here, because XA plus XB is equal to 1. Now, for GA0 at a known temperature pressure, GA0 means of the pure phase. If we have, this is A pure, this is B pure. So let's say this is a point where you have GA0, and for B at a particular point you have GB0. Right? At a known pressure and temperature, for pure A, we'll have a particular GA value. For a pure phase, of course, activity is equal to 1, and so it could be GA, but I have written it as GA0, of course, which is equivalent to GA. Why? You can ask me, so why didn't you write GA? It's because it is the free energy of a pure phase. So GA0 is the right symbol for it. If we do this, then if we take now a mechanical mixture of A and B, like salt and sugar, right? Salt and sugar. Or in the liquid state, oil and water. If we make a mechanical mixture, again meaning very clearly that from that mixture or from that, I can physically separate A and physically separate B because of certain characteristics. Right? We can separate A and we can separate B. So now, if I write a term, G mechanical mixing, what will be the G of the mechanical mixture of A and B? Obviously, it would lie on this straight line. It would lie on this straight line. I will write this a little lower. Sometimes it's difficult to show it because of the curvature. And this is the straight line. Now, G mechanical mixing. So at any particular point here, say for example, this is the value of XA, this is the value of XA, and this is the value of XB. This is the value of XA. And this is the value of XB, just as in Lever's rule. So now what we have is, if we want to find out the free energy, which we mean this value is the free energy value, what will be the free energy value? The answer is very simple. You have XA into GA0 plus XB into GB0. This is what it will be. The mechanical mixture, if I take it at any particular point, then the mechanical mixture of that point, the free energy of the mechanical mixture, should be XA/GA0 plus XB. That means this is XA into GA0, XB into GB0. I'm saying Lever's rule, but you had an igneous petrology course. So once you have an igneous petrology course, these are not to be repeated. These are taken at random automatically. The phase diagram stands on Lever's rule. Right. So this is G mechanical mixing. Now say, if I do what is, let's say let me write, what happens, this is for a mechanical mixture. What happens if there is a solid solution between A and B? What is the difference? Solid solution of A and B. What does it mean? It means that A and B now in the solution cannot be separated physically. It's a homogeneous solid solution where A and B lose their identity, separate identity, which is preserved in the mechanical mixture. But when I talk of a solid solution, it is between two n-member molecules, but the molecules lose their own distinctive properties. And for that, the G solid solution will be lower than the mechanical mixture. Why? It's very simple. Because if you are taking a solid solution, then activity A term is added and activity B term is added. Now activity is not equal to 1 but less than 1. So GA will be less than GA0 and GB will be less than GB0 at any particular composition. At this composition, it will be back. These two terms will be unity, and therefore this is equal to this. So the solid solution between A and B should lie below the curve and not above the curve because of this reason. Because for an impure phase, such as a solid solution, the activity of A has a value lower than 1. If it so happens, then the free energy of the solid solution should lie lower than that of the mechanical mixture. Right? So let's say we take this curve as a solid solution. This is for the mechanical mixture, GMM, and this is GSS, solid solution between A and B. Now you can see here that for any particular composition, here you see there is this drop here. Have you understood? So if you write G solid solution, then I need to write it as, how will I write it? I can write it as, you see here, I can write it as, look at here, XA GS0 plus XB GB0 plus G mix, where this is G mix. So I take this term and drop this value. You can say, so why is it plus? It should be minus. Because G mix itself is negative. G mix is itself negative. So you can't have a negative of negative. You can write plus G mix because G mix itself is negative. So this is how G solid solution can be written in one way. For any, and you can see this G mix value is not constant. It is a function of the composition. So the G mix value here is a function of the composition. Only at the two n-member points, G mix is 0. Of course. Why? Because GA is equal to GA0. Why? Because activity is equal to 1 for the pure phase. So the G solid solution curve is pivoted at the two end members, but is lower than the mechanical mixing curve. And how it can be written is G mechanical mixing, this point, plus the negative G mix. And this is how it is done. But the G solid solution can also be written in another way. What is the way? Here, let me draw it. I take this point and draw a tangent to it. Have you understood? I draw a tangent to it at this point. Remember, this line is like this. If I shift the point here, then the line is like this. If I shift the point here, the tangent is like this. So now, what is the two end members of the tangent? This is GB and this is GA. This is GB and this is GA. But unlike GA0, which is fixed, this tangent will change its slope. This tangent will change its slope dramatically depending upon the point that you are taking. So now we have a situation. This is a difference and this is a difference. So if we take the tangent now, then I can write G solid solution now. Now, if we consider the tangent only, you can write XA GA plus XB GB. Do you see? The same way we wrote for mechanical mixture. In the same way that we wrote for the mechanical mixture. So now we can equate both equations. They are both same. Now, before we go into that manipulation, let me tell you one thing. The GA value is not fixed. The GB value is not fixed. This tangent, which has this slope now, can move up and down depending upon where your composition is. So the Gmix value and GB and GA value are all compositional variables at this pressure temperature condition. There are also functions of pressure and temperature, but if you have to understand solid solution, you may see it at a particular pressure. If you change all variables, it will become very complex. So at a particular pressure temperature condition, which are also variables, but at a known pressure temperature condition, these two variables will change its slope. They are functions of composition. Having said this now, we can write XA GA plus XA GA plus XB GB is equal to XA GA0 plus XB GB0 plus Gmix. So if we write this, then we can write what is Gmix? What is Gmix? Gmix therefore is equal to XA GA minus GA0 plus XB GB minus GB0. This is where we reach. This is where we reach. Mark here this one. Mark here this one. So what happens is, therefore we can write RT, we can also write RT XA ln activity A plus XB ln activity B. Why? Because GA minus G0 is equal to RT ln activity A. So we can write this down. Have you understood? I think I give you 2 minutes time to think over it. There's nothing to... Now, this value, this GA minus GA0, GA0 at a particular temperature is fixed, but GA is varying. But GA is varying. It's a function of the composition, as you can see here. This is like a steering wheel of the car. It would depend where you are drawing the... So say, for example, if this was your x value, then the slope of the tangent would have been like that. If this would have been the value, the slope of the tangent would have been this. And in all three cases, all will be GB. But GB0 is fixed. And this is a function of the composition. So we have this type of a situation. What is Gmix therefore? Gmix. This one, what is Gmix? RT, constant, XA into ln activity A, XB into ln activity B. Now we know that Gmix should be 0 at pure A. Gmix should be 0 at pure A. Let's see whether it's right. At pure A, XB is equal to 0. So this term vanishes. And please see here, Gmix should be 0 at pure A. Pure A means XA is equal to 1. So if XA is equal to 1, it will be ln activity A, but ln activity A will be equal to 0 because it's a pure phase. So this term becomes 0. And this term remains. Here, xb is 0. Do you see that? xb is 0. So G mix is 0. Similarly, if you go to the B end member here, you see at B end member, xa is equal to 0. So xa is equal to 0. So this term vanishes. xb is equal to 1. Yes, of course. But activity of B is 1. So ln of 1 is equal to 0. Again you have 0. But the point here that I'm trying to make, it is at the end members it's 0, but at the intermediate ranges, G mix changes as this term. Can you see that? It is this term which changes. Have you understood? Right. I will just erase the top because there is hardly any space on the board. So, now there is an important thing when you, just before we go into the next step, we know that RT ln activity A is equal to RT ln xa plus RT ln gamma. Similarly, RT ln B, sorry, RTL and gamma B. We know this. RTL and XA plus RTL and gamma A. If I break up this term, it's RTL and XB plus RTL and gamma B. Now, we need to understand a little bit more of this. What is RTL and XA? Let us assume RTL and gamma A is 1. Let's say RTL and gamma A is 1. Means it's an ideal solution. Yesterday I talked to you about it. Where gamma is equal to 1, it's called an ideal solution. So, what is RTL and A is the effect of ideal solution. Have you understood? And what is RTL and gamma A? Non-ideality or excess ideal mixing. This getxa is because of ideal mixing, and this is called excess mixing. This is called excess mixing. Have you understood? That's very, very important. If I just write RTL and XA, then it means RTL and gamma is equal to 1. That means ideal solution. So this part essentially represents the energy for ideal solution. And what is this part? This is something in excess of ideal mixing. It could be negative, it will always be negative or positive or whatever it is. You know, it will be positive for positive solution of ideality where gamma is greater than 1. Yesterday we talked about it. It would be a negative deviation from ideality if gamma is less than 1. So gamma values can be of positive or negative or 1. 1 for ideal solutions. But XA is either 1 or 0 or less than 1. So RTL and XA term is always negative. RTL and A term is either 0 or negative. RTL and gamma term can be positive for gamma greater than 1, negative for gamma less than 1, and for equal to 1, it's ideal mixing. So, when we talk of RT that there is only RTL and XA, we have ideal mixing. And when we have gamma A, it is called excess mixing. That excess mixing can be positive or negative. But why the term excess? Why don't we, you can ask me, sir, why don't you say non-ideality? Non-ideality includes both ideality and non-ideality. Have you understood? The whole thing together is called non-ideal. I want to designate a name for RTL and gamma A. And that is designated by people as excess mixing. More than ideality. More than ideal energy considerations. Which could be positive, one, or negative. One is for ideal mixing. Now, if that is the case, then we can do a few things from this equation. We can write that G mix is equal to XA, same as here. Oh. Do you understand? So we can break up G mixing as XA into mixing of A and XB into GBX of mixing of B component. There are two components. We can also write it in that way. So the G mix here comes from two components. One is G mix A, which is nothing but RTL and activity A, and G mix B, which is RTL and activity B, or the XB minus GB0 is G mix. It doesn't matter. But, so it can also be written like this. There is no contradiction here. Then what is G mix A? G mix A is equal to GA minus GA0 is equal to ln activity A. Same. Now therefore, we do one more last manipulation of this. I'm not going to go for the derivations because this I have already given you and you should be knowing it. So we can write now, you can see GA minus GA0 is equal to RT ln activity A. This we know. And GB minus GB0 is RT ln activity B. Now, this part we can manipulate a little bit. Let's see what is happening. What have I done? The catch here is of use of this term. Now you see here. This term GA is here. I have introduced it as minus G ideal. And this one, the negative sign stays. The negative sign stays. And I have written GA0 minus G ideal. So what happens? Here, G ideal is negative, and if you break this bracket, then G ideal is positive, so it cancels out. And equation goes back to GA minus GA0. So the manipulation here is very simple. This part has been divided into two parts. One is for the pure event member minus G ideal, and for GA minus G ideal, two parts. I have broken it up. Now, also on the right hand side, I have broken up RTL and activity A into RTL and XA, RTL and gamma A. Now, you must remember, I can do the same thing for the B component. I can do the same thing for the B component. I'm sure that you understand how to do it. GA, here I have done it for the A component. Same manipulation can be done for the B component. Now, why I have done this? Remember I told you when you have RTL and XA, that means RTL and gamma A is 1. When you just write RTL and activity A is equal to RTL and XA, then you actually mean RTL and gamma A is non-existent. That means it's 0. That means gamma is equal to 1. So then you can see this term here or this term here, for example, is the same as this term. Do you see that? GA0 minus G ideal is RTL and XA. And RTL and gamma A is the term which is this. I'll give you 1-2 minutes to think about it. Think about it. There is GA0 minus G ideal. Forget this part. If I have to write this, then this should be equal to RTL and XA. Because XA, when you say at XA, then you mean gamma A is not 1. Is 1. But if there is gamma A, then this should go under GA minus GI ideal. So essentially what you do is, in this diagram, right? So this is the free energy of ideal mixing, and this is excess mixing. So what happens is, you can write, this is what I was trying to tell you, GA minus G ideal is equal to RTLN gamma A. This also can be written as G excess mixing of A is equal to G excess mixing of A is equal to GA minus G ideal is equal to RTL and gamma A. A similar equation can be written for B. A similar equation can be written for B. Tell me, have I been able? I don't know how you can tell me, but this is what it is. In the lecture, in the printouts that I gave you, I just derived the equation. I didn't give you the logic. Sometimes it's not possible to give every point of the logic when you're reading a book. But here, that is why I took this class, so that you understand part 2 more clearly. So you have RTL and XA. This is the ideal mixing component, and that is why you have GA minus GA0 minus G ideal. And this gamma term is GA minus G ideal, excess mixing term. G excess mixing of A is equal to GA minus G ideal is equal to RTL and gamma A. This is the excess terms. This is more than ideal. This is over and above the ideal. But it could be negative depending on gamma. If gamma is less than 1, this term will be negative. If gamma is more than 1, this term will be positive. But this term will always be negative. Always be negative, because it's RTL and XA. Only for a pure phase, XA is equal to 1, will this term be GA0 minus G ideal. It should be equal to 0. That means GA0 is equal to G ideal. GA0 is equal to GA ideal will happen only when RT ln XA is equal to 1 for a pure phase. So this is what we have. Now, I don't have more place to write, so I don't know how to do it. I will sort of erase this part. So this is how excess mixing is. So now I will try and erase this part. So now we have a situation, therefore, where we have, what was I talking about? Here. So we have G excess mixing of A is equal to RT ln gamma A, and also you can understand G excess mixing B is equal to RT ln gamma B. Now this G excess mixing term can be very complex. This excess mixing term is done from experiments. These are theoretically very poorly developed. You can do it theoretically, but most of the more demanding ones are experimental drop calorimetric experiments from which you can find out free energy of solid solution. Once you find out the free energy of solid solution, then you can model the free energy of solid solution, and you can find out excess mixing terms. It's a little complex, but you can find out the excess mixing term. In fact, in most solid solutions, these are determined wherever some amount of experiments were available. Where no experiments could be done, these people have tried to estimate based on theoretical determination and trying to tally one with the other and trying to arrive at some sort of a coherent value which is meaningful. But the important part here is that G excess mixing is equal to RT ln A, Y excess mixing, because GA minus G ideal. GA minus G ideal. That means the difference is something that is more than ideal mixing, added to the ideal mixing term. You know, this GA ideal mixing, it was added to the ideal mixing term. So that's very important to realize. So this is GA excess mixing term. Now this GA excess mixing term can become very complicated. But a very simple way of doing G excess mixing, one very simple mixing term for G excess mixing, say for example, is written as, this is called WA XA into XB. This is one very simple way of doing things. This is called symmetric regular solution behavior. This is more complex. You don't have to understand a lot of it now. Right now it could be done for those who are doing the research in metamorphic petrology. They could try and work on it. So these are called, these terms, they look like this. I will erase this part of the diagram. I can't use the board anymore. So essentially what happens, if you have taken a component and a B component, now you can see, say for example, the size and charge of A and the size and charge of B, like say we had written Mg2SiO4 and Fe2SiO4, and magnesium was 0.66 angstroms and iron was 0.74 angstroms. So you can see they are reasonably of small size, similarly of similar size. But if you take, for example, a mineral called Ca2SiO4. Now I don't know whether you know the name of this mineral, which is also called an olivinoid. the name of the mineral is Larnite, is called Larnite. Larnite, Ca2SiO4. Ca is 0.99 angstroms. So you can see that magnesium and iron can be replaced in the site, but there is a very small difference in the structure. It will cause small distortions in the structures. But if I would like to replace magnesium by calcium or iron by calcium, it's not easy because they have very large size difference. So if I want to make a solid solution between forsterite and Larnite, then it would cause a large distortion in the structures. Have you understood? Say, for example, if I want to replace magnesium by calcium or calcium by magnesium, the energy exchange that is required is highly unequal. Have you understood? If you have magnesium small and you want to replace it by calcium large, or if you have calcium large and a small magnesium ion, the structures have to adjust very delicately, and there is a large difference of structures, and this energy exchange is normally given by this term called W. And this W term was designed by a very famous person, and they are called Margules parameter. Margules parameter. These days they are called interaction parameters. Interaction parameters. How are they designated? They are designated as W, AB, and then the phase alpha or beta. Same as this. W, AB, phase alpha or beta. If they are different, it's for you, it's just for the information. You write W hyphen AB alpha, W hyphen BA alpha. So what happens in this case? Here it means A replacing B, and here it means B replacing A. They could be also very different. They could be very different. But in this, where you have WAB only, I will correct it, it is wrong. WAB only, then it is called symmetric. That means it's typical for, say, for example, Mg2SiO4 and Fe2SiO4, where the two charges are very similar. So if you want to replace magnesium by iron, or you want to replace iron by magnesium, the interaction energy that is required to exchange is small. As different when you replace forsterite by Larnite. They don't form a solid solution. We will come to that question in a moment. So that is what is very important to realize, that the magnitude of WAB, which is the Margules parameter or the interaction parameter, the magnitude of this value is small when the competing cations are very similar in charge and size. But when you have two cations, nearest neighbor cations, that replace each other, but they are widely dissimilar in charge and size, then the interaction parameters are very high. So a typical case is when you have charge difference. I will just give you one more example. Say you have CaAl2Si2O8. This is anorthite. And you have NaAlSi3O8. This is albite. Anorthite and albite. This is 2 plus, this is 1 plus. But calcium has an ionic radius of 0.99 angstroms and sodium has 0.97 angstroms. So you see, size-wise, they are very, very, very similar. So the interaction energy theoretically, if you look at just the size, should be very small. But it is not. Why not? Because if you replace sodium by calcium or calcium by sodium, then there is a charge imbalance from 2 plus 1 to 2 plus 1, and that has to be accommodated by redistributing aluminium and silicon in the tetrahedral site. This is called the tetrahedral site. So what happens? The actual exchange reaction is Na plus Si, 4 plus, is equal to Ca2 plus plus Al3 plus. Now, you see, although the charge difference or size difference is very small, but there is a huge charge difference of 50%, which needs to be compensated by replacing silicon and aluminium. And replacing silicon and aluminium is one of the most complicated things in silicate minerals. Therefore, this W parameters in plagioclase have very large W values. So for cations having similar size and similar charge, W values, molecules parameter or interaction parameters are small. If they are identical, when you get ideal mixing. When the interaction parameter, when the ionic size and the charge of the two competing cations are identical almost, then W values are 0. That's where, when W values are 0, G excess mixing is 0. Therefore, RTL and gamma is equal to 0. Therefore, gamma is equal to 1. That's what's the theory of ideal mixing. That excess mixing is 0. Excess mixing is 0. That is the important thing. When two cations of same ionic radius and same charge, they interact, you do not require any amount of energy to move them. It's very small or close to 0. So when you have W values close to 0, excess mixing is close to 0. If you have excess mixing close to 0, you have gamma equal to 1. You have ideal mixing. Otherwise, you have non-ideal mixing. So, if someone asks you which systems have non-ideal mixing, the systems where the size of the charge, size or the charge or both differ greatly. That's the theory. So, now that we have reached this point, we can now write we assume we take our excess mixing term. We take our excess mixing term for this very simplest and simple case is where WAB into XA into XB. So what happens also, you will see in your write-up, there's a derivation how to find out gamma A and gamma B from G excess mixing. The whole derivation is given. I don't need to do it. It's correct. It's done there. So now from this we can write, if we now put in the actual things, so you have XA into GA0 plus RTLN XA plus RTLN gamma A. GA0 plus this plus XB is equal to GB0 plus RTLN XB plus RTLN gamma. Done? And then we can take out everything and we can write three terms. XA GA0 plus XB GB0. We have taken away this term and this term. So we can write it like this. Then we take out plus RT XA ln XA plus XB ln XB. So we have taken out this term and this term. And then we take out plus RT ln XA ln gamma A plus XB ln gamma A. That's the three terms that we're taking. This, you will recall, is G mechanical mixing. This is G ideal mixing. This is G excess mixing. This is how the equation is of a free energy of a binary solid solution. There are three terms. One is the free energy of mechanical mixing. Then you have XA ln XA, XB ln XB plus RT, G ideal mixing. And then we have RT XA ln gamma A, XB ln gamma E is equal to G excess mixing. This is what we have done. So, if we take it upstairs here, we can read we can write G solid solution is equal to G mechanical mixing plus G ideal mixing plus G excess mixing. For a binary solid solution, for all solid solution, all binary, ternary, quaternary, whatever solid solution. This is the theory. G mechanical mixing plus G ideal mixing plus G excess mixing. For a binary system, it turns down to XA GA0 plus XB GB0, XB GB0 plus ideal mixing RT XA ln XA plus XB ln XB plus RT XA ln gamma A plus XB ln gamma A. We can also write XA GA0 plus XB GB0 plus RT XA ln XA plus XB ln XB plus W AB XA XB. This is a model. Not all terms are like this. It can be very complex. This function can be very complex. But we're looking at a binary and we take what is called a simple regular solution. The name of this is simple regular solution. Or it's also called symmetric. I will explain it to you in the next class. Symmetric regular solution model. Now, I will stop here for now because after that I think I have to take one more class to tell you the effects of this. Just one small thing. This term you see here, this term is always negative because free energy is a negative term. H plus A is equal to a negative term. So this is always a negative term. This term, you see XB, ln X, XB, XA, all are less than 1. So ln terms are all negative. This is also a negative term. But it is multiplied by temperature. So it's a negative term but increases with T. It's a negative term. Overall, this is a negative term. But this, the negative magnitude of the negative value increases with temperature. Negativity increases with temperature. And this term can be positive, it can be negative, it can be W can be positive, W can be negative, W can be 0. We will see the effects of it in the next lecture. For the moment, I think till here, this is your what should I say, content for the February 9th class. We will go here, till here is your class, including all those PDFs that I said, all those are included, and so this is where we stop. The effect of this is very, very formidable, and that I will tell you in the next video lecture. So long, thank you.